This is my Thermo system design final project on external combustion in the Stirling and Ericsson engines. External combustion is a fascinating concept, and it develops power output using only two thermal reservoirs. And it's colloquially named external combustion since there's no actual combustion reaction. So two common examples of this are the Stirling and Ericsson engines that you can see the graphs for below, and our goal in this project is to duplicate the power output of a commercially available portable generator, which uses a 49cc Otto cycle engine. So the theory of the Stirling and Ericsson engines is that there's two spaces made by two pistons. There's a compression space and expansion space, as we see below there. And basically the Thermo system operates within the compression space and is relative to everything going on in the compression space. The main difference between the Stirling and Ericsson engines are just that the Stirling engine uses isochoric heat addition rejection, whereas the Ericsson engine uses isobaric heat addition rejection, and both use isothermal compression and expansion in the ideal case. So we did a parametric study in ease to find ideal parameters to run the engine at, and we came up with 5,000 cc or 5 liters for the cylinder size, a compression ratio of 15, and a temperature difference of 500 degrees. Since thermal efficiency only depends on temperature, compression ratio, and cylinder volume had no effect on efficiency, but we looked at the network change. Many of the logarithmic trends help to show drop-offs and gains for the network and thermal efficiency, and these were used to find ideal parameters. So here are our results with the ideal parameters. We can see that the Stirling engine makes more power, and they both have the same exact thermal efficiency since they're both running between the same temperature difference. And we can also see the isochoric and isobaric processes like we talked about earlier. So the conclusions are that the Stirling and Ericsson engines both need a large volume to compete with some other practical engines, such as the Otto cycle engine currently used in the generator. Therefore, they're best used as regenerators in existing systems where space isn't a limitation, and thermal reservoirs can be easily supplied with heat, such as in the exhaust steam of a power plant. So it has about 100 times the volume of a gas engine, and it produces less than 10 times power. Although it does have higher thermal efficiency than most other engines, even ideal cases. But this is still limited by our assumptions, which are likely untrue, about the isothermal compression expansion and the heat transfer assumptions, which leads to lower power output at a lower efficiency. Also, 500-degree temperature difference is difficult to achieve without another source of energy, such as in the steam power plant, making solar energy very impractical to use for this application.